So typically you're used to representing graphs as a collection of points x, y on the rectangular Cartesian coordinate system that looks like a grid. But in this section we're going to study another coordinate system that you can use, and it's called the polar coordinate system. So the polar coordinate system is based on angles in circles. So basically we have this fixed point, which we call the pole, or you're used to calling it the origin. It'll land in the same place that the origin normally lands. And we construct an initial ray from the origin, and we call that the polar axis. Now the polar axis is going to lie in the same position as the positive x-axis would lie. And then we look at all of our points as a directed distance from the origin and a directed angle from the polar axis, going counterclockwise. So this point here, P, is represented by the distance between O and P and the angle that is formed between the polar axis and the line segment OP. Now in the system, it can help to use a grid of concentric circles to graph points instead of rectangles, because you can count out the r distance pretty easily that way. So for example, this point would be 2 comma pi over 3, and the order doesn't matter. R always comes first, r theta. So you would count up to the angle pi over 3, and then along that line you would count 2 units using the circular grid here. This one would be 3 negative pi over 6, so we would count down to the negative pi over 6 and out 1, 2, 3 and land at this point. And then here we have 3 comma 11 pi over 6, so we're going to count in this direction because it's a positive angle. You notice it's the same exact point as this particular point. So these two are two different coordinates that represent the same point. So this is an important distinction because for rectangular coordinates, every point is unique and only has one way to represent it. But this is not true for polar coordinates because you can have angles that are different but represent the same space. Those are called coterminal angles. Or you can also have to consider the way that you handle negative values of r. So if I have a point like, for example, say this is my circular grid, and I'm going to show you some of my horrible artwork right now. I'm not an artist. But this is my circular grid. And say I want to graph the point -2 7 pi over 4. So 7 pi over 4 goes around the circle and is here. Okay. But when you have a negative value here, instead of going in the positive direction 2 units, you're actually going to go away from the angle. So this is 7 pi over 4. I would actually want to go in the opposite direction of that angle and count 2 units that way. Now this same point could also be represented by using the angle 3 pi over 4 and counting towards 3 pi over 4 in the positive direction 2 units. So we have two different representations of the same point. So a couple of ways that this happens is obviously with coterminal angles, like in this case, if you add 2 pi to the angle, you have the same point if r stays the same. But also, if you add pi to the point and change the sign of r, you end up with the same point. So this would be an example of that case. You can also convert your coordinates, and we can do that using some pretty simple formulas. So just to kind of illustrate where this comes from, this is the pole and the polar axis, and we've got our theta here, r theta, x, and we've got a point x, y in rectangular coordinates. So one thing to keep in mind is that if you're looking at this is a right triangle with the right angle here, the sine of theta would be the opposite over the hypotenuse, so that would be y over r, and the cosine of theta would be the adjacent over the hypotenuse, which would be x over r. And if you solve these for x and y, you get y equals r sine of theta, and you get x equals r cosine of theta. And those are the conversions that we're going to use to convert between polar and rectangular coordinates. X equals r cosine of theta and y equals r sine of theta. If you want to go in the opposite direction, you can use some relationships here. This is the tangent of theta is equal to y over x. And you can verify that using these two conversions here, because we know that tangent of theta is sine of theta over cosine of theta. So that is y over r divided by x over r, or just y over x. So you can see where that comes from. This one right here comes from, if you take x squared and plus y squared, and you plug in these versions of it, you would get r cosine of theta squared plus r sine of theta squared, which would give me r squared cosine squared of theta plus r squared sine squared of theta. And if you factor out the r squared, you get cosine squared of theta plus sine squared of theta. And of course we know that this is just 1 by the Pythagorean identity. So these are all easily verifiable using these conversions here if you ever forget them or you aren't sure. So this is to convert the polar coordinates r theta equals 3 pi over 2 to rectangular coordinates. So let's make sure we know the order here says that r is equal to 3, theta is equal to pi over 2. So x is going to be r cosine of theta, which is 3 cosine of pi over 2. And if I glance back quickly at my unit circle, I know that for pi over 2, the cosine is 0, so this is just 3 times 0, or 0. Y is going to be r sine of theta, so that'll be 3 sine of pi over 2. And glancing back at my unit circle, I know that sine of pi over 2 is 1, so that'll be 3 times 1, or 3. So the coordinates in rectangular coordinates x, y are 0, 3. This one we have r equals the square root of 2 and theta equals pi over 4. So x will be square root of 2 times cosine of pi over 4. And of course the cosine of pi over 4 is root 2 over 2. So this gives me 2 over 2, or 1. Y is going to be the square root of 2 times sine of pi over 4, which is root 2 times root 2 over 2, which is also 1. So the xy for this problem is 1, 1. Now this one we're given x and y, and it wants us to find r and theta. So we're going to go in the opposite direction. And remember, we were advised to use the tangent of theta equals y over x, and the fact that r squared equals x squared plus y squared. So for this one, I know that the tangent of theta has to be negative 1 over 1, or the tangent of theta equals negative 1. And there's a couple different ways that you can do this. You can go to your unit circle, or if you remember your special 30, 60, 90 and 45, 45, 90 triangles, you can use that as well. Any method that you've used for solving a trigonometric equation is valid. So I recognize that that my special 45, 45, 90 right triangle has the ratios 1, 1 squared to 2. And that would normally give me that tangent opposite over adjacent is 1. So if I put this thing in the coordinate system, I know that tangent, the inverse tangent, theta is the inverse tangent, or the arc tangent of negative 1. I know that that answer is going to lie in one of these two quadrants because that's how it's defined. And since all sine, cosine, and tangent are positive in the first quadrant, I know it's got to live down here. And I know the reference angle has to be 45 degrees, or pi over 4. So that means that this particular theta, in order to make this negative, has to be negative pi over 4. So it lies in that quadrant. Now similarly, I need to know how to find r. And I'm going to use, I want a positive r. So I know that r squared is going to be 1 squared plus negative 1 squared. So r squared is 2, and r is going to be the square root of 2. So my polar coordinates are going to be √2 and -π/4. Yeah, you may have some specific problems that say express your theta between 0 and 2π, and if that's the case, all you would need to do is add a 2π to that. I'm not really picky about it, but sometimes WebAssign is if they give you specific instructions on that. Here's another one. We have x equals -1 and y equals -3. So the tangent of theta is -√3 over -1 or √3. And this is another that comes from a special triangle, the 30, 60, 90. And we know that the ratio of that is 1, 2, and the √3. So I can say that tangent of π/3 gives me the opposite over adjacent as the √3. Another way that you can think of the angles when you're given these types of coordinates is if you graph the thing approximately, or at least if you know what quadrant it's in, you know what quadrant your angle has to lie in also. So this one has to be in the third quadrant in order to make this work. So I know that it needs to be whatever angle has a π/3 in this quadrant. So theta in this case is going to be π plus π/3, which gives me 4π/3. So there's a couple of different ways you can go about solving that. R is going to be the square root of x² plus y², which is the square root of 1 plus 3, or 2. So my polar coordinates would be 2 and 4π/3. Now when it comes to graphing polar equations, one thing that we like to do with this sometimes is to convert from polar coordinates to rectangular coordinates and with the equation, and actually graph whatever we find as our equation. So to do that, you take a very similar approach to what you do with coordinates. It's just you're converting your equations instead. But we're going to use those same 4 rules. X equals r cosine theta, y equals r sine of theta, tangent of theta equals y over x, and r² equals x² plus y². So for this one, I have r equals 2, and what I'm going to do is I'm going to square both sides and get r² equals 4. And I know that r² is equal to x² plus y². So this gives me the equation x² plus y² equals 4. Now I recognize this as being a circle with a center at the origin 0, 0 and a radius as the square root of 4 or 2. X minus h² plus y minus k² equals r². So I know that this graph is a circle with a center here and a radius of 2. And just pretend I traced that circle nicely. So anytime you have r equal to a number, it's going to follow this same pattern. R equals to a number is always a circle centered at the origin with that radius. So hopefully that's starting to give you an idea of what polar coordinates actually represent. R is the radius of a circle. Now this one says r equals 3 secant of theta. So let's be a little careful with this one. This is the same thing as saying r equals 3 times 1 over cosine theta, because secant of theta and 1 over cosine of theta are equal. So what I can do then is I can take this equation and I can multiply on both sides of the equation by cosine of theta. As long as I do it to the same thing to both sides, that's perfectly legal. And that cancels these two cosine of thetas, and I get r cosine of theta is equal to 3. Now why am I interested in that? Because I know that r cosine of theta is the same thing as x. So this is saying x equals 3. And I know that x equals 3 is a vertical line, 1, 2, 3, through the point 3, 0, and just going up and down. Now with this one, I have theta equals π/3. So if I have theta equals π/3, the only equations that involve theta are x equals r cosine of theta, y equals r sine of theta, and tangent of theta equals y over x. Now I know how to find the tangent of pi over 3. The tangent of pi over 3, using whichever method you're comfortable with, is the square root of 3. So I have the square root of 3 equals y over x. And if I multiply both sides by x, I get y equals the square root of 3 times x. Now this is a straight line. It has a y-intercept of 0 and a slope of the square root of 3. So I'm going to roughly trace this out for you. It's going to look like this. Now this is the line that goes through theta equals pi over 3 in the unit circle. So it's a 60-degree angle. So that shouldn't be quite a surprise. Okay, let's just do some more conversions, not graphing. I've got r equals 6 cosine of theta. Now I don't have the r here yet, and I can't move anything around to get it just yet. But what I can do is I can take this equation and I can multiply both sides of it by r. That's perfectly legal because you've done the same thing to both sides of the equation. On the left, this gives me r squared, and on the right, I have 6r cosine of theta. So now I can replace the r squared with x squared plus y squared, and I can replace the r cosine of theta with an x. So that gives me x squared plus y squared equals 6x. Now if you were trying to graph this thing, you might not be perfectly clear on what this thing looks like. So this is where some algebra can come in handy. If all you need to do is convert, this is a valid answer. But if you want to know a little bit more, you can do what's called completing the square. I'm going to move this 6x to the left-hand side, and that'll leave me with a 0 on the right. And notice it turns negative. And remember, to complete the square, you take the middle term, whatever it happens to be, and you half it. So that would give me negative 3, and I'm only looking at the number here. So negative 6 over 2 is negative 3. And I'm going to add the square of that to both sides of the equation, balancing it out. And then I'm going to factor this, which gives me x minus 3 squared plus y squared equals 9. So while the other equation is perfectly valid, this one is better because it's in standard form. This is a circle. It has a radius of 3 because the 9 here is 3 squared, and it has a center of 3, 0. Now if you don't remember how to do this process, go back to your Math 112 or your high school Algebra 1 or 2 notes and check out completing the square and the equations of circles. Plenty of videos on YouTube as well. This one is very similar to one that we did earlier. R is equal to 5 over sine of theta because cosecant of theta and 1 over sine of theta are the same thing. And then I multiply both sides by sine of theta, and I get r sine of theta equals 5. And I know that r sine of theta is y. So this is just the horizontal line, y equals 5. What you'll notice is some equations are more simple written in polar coordinates, and others are more simple written in rectangular coordinates. Polar coordinates are good for things that have lots of nice round circles and curves and anything that's based in that circular grid really well. Rectangular coordinates tend to look better when you're looking at things like lines and things like that. Okay, so let's do a little bit more conversion. So with this one, I've got x equals 3. And if I wanted to convert this from rectangular to polar coordinates, I'm going to turn the x into r cosine of theta equals 3. And your goal is to either get theta equal to something or r equal to something. So r is usually the variable you're going to be solving for. I'm going to divide both sides by cosine of theta. and I get r equals 3 divided by cosine of theta. There's nothing wrong with that, but you can write 1 over cosine of theta as secant of theta. So I'm going to leave this as r equals 3 secant of theta. With the next one, I've got y equals 7. Remember, y is r sine of theta. So I'm going to pull the same trick I did before. I'm going to divide by sine of theta. And I get r equals 7 over sine of theta, which I can write as r equals 7 cosecant of theta. Now with this one, I'm going to start by foiling out this square here. That'll give me x squared minus 4x plus 4 plus y squared equals 4. So now what I'm going to do, I'm going to cancel the two 4's. I've got x squared plus y squared, and I'm going to add 4x to both sides. So I get x squared plus y squared equals 4x. Now with one like this, I can write the x squared plus y squared as r squared, and the 4x as 4 times r cosine of theta. Now here you may be tempted to go ahead and divide by r, and as long as you don't have to account for the possibility that r equals 0, that's perfectly fine. But typically we would go ahead and move that back over. We would factor out an r, which leaves me with r minus 4 cosine of theta. And then we would set each of those equal to 0. So I would have r equals 0 or r equals 4 cosine of theta. And this is the one that usually gets referenced because this one's kind of a trivial solution. With this one, I'm going to convert the x to be r cosine of theta and the y to be r sine of theta. Then I'm going to factor that r out, which will leave me with 3 cosine of theta minus 2 sine of theta. And I'll have a 1 on the right. And then I'll divide to get r equals 1 over 3 cosine of theta minus 2 sine of theta. So that will be my answer.